Hello everyone, we are Group 1 and this is our presentation for the Internal Combustion Engines Lab, Part 2. The objective of this lab is to test the validity of our work kinetic energy model through each stroke. To start our analysis, we must first understand each stroke of our engine. During the intake stroke, air is taken into the cylinder through the intake valve while keeping the exhaust valve closed. During compression, both the intake and exhaust valves are closed as the air inside the cylinder is compressed towards the highest point of the piston's travel. This point is known as the top dead center, or TDC. During the power stroke, compressed air is going to be forced into the cylinder next week during Part 3 to resemble the explosion that is normally created with an air-fuel spark mixture. The piston will travel to its lowest travel point, also known as the bottom dead center or BDC. During this process, both the intake and exhaust valves remain closed. During the exhaust stroke, air is released out of the cylinder through the exhaust valve while keeping the intake valve closed. Looking at the graph, we can see that to go through one cycle of our 4-stroke IC engine, the piston displacement will go through 2 total cycles. From 0 to pi, it's the intake stroke. From pi to 2 pi is the compression stroke. From 2 pi to 3 pi, the power stroke. And finally, from 3 pi to 4 pi, the exhaust stroke. Our first step was obtaining a calibration equation. With the data provided, a regression line was performed, resulting with the calibration equation on the screen. During Part 1 of this lab, we learned that the change in kinetic energy is equal to the work done by the motor, air, piston, friction, and error. Since the head of the motor was removed, we were able to neglect the work on air. Also, the displacement of the piston head was found to be relatively small, so the piston work is assumed to be 0 along with the work error. Using the work of the motor, torque, angle change, and the angular speed, we were able to calculate the inertia of the flywheel. This is done by accelerating the motor from rest in 2 different cases. In the first case, the motor has 4 flywheels attached, and in the second, only 1. Since we are starting from rest, we can say that omega fly at point A is 0. Therefore, the work energy kinetic model is equal to equation 2 on this slide. We know all the variables needed to calculate I-fly for each case, since omega fly is equal to the derivative of the angular position versus time graph. But first, we need to understand what I-fly actually is. I-fly for this equation is really the moment of inertia of the flywheels combined with the internal shafts and gears. Therefore, we need 2 acceleration cases because the moment of inertia of these internal parts cannot be solved analytically. To find the moment of inertia of one flywheel, we must subtract the moment of inertia of one flywheel plus the internal components from the moment of inertia of 4 flywheels plus their internal components. This way, the internal components' moments of inertia will cancel out and leave us with a number that is equal to 3 times the actual moment of inertia of an individual flywheel. Now, to find the moment of inertia of an individual flywheel, we simply divide that value by 3 and get the experimental moment of inertia is equal to 0.0022 kilograms per meter square. The theoretical moment of inertia of a flywheel is found by assuming that the flywheel is a solid disk and using the equation to solve its moment of inertia that way. This was found to be 0.002485 kilograms per meter square, which means our experimental values has an error of 12.9%. The biggest difference between Part 1 and Part 2 of this lab is that now we are reattaching the head. This means that our work kinetic model needs to be adjusted as W air cannot be neglected. During the intake and exhaust strokes, the valves are open, so for those strokes, we can neglect W air. Without pneumatic injection, we can assume that the work in the compression and power stroke are the same in magnitude but opposite in sign. The value for work air in the compression and power stroke is equal to the integral of the pressure with respect to the volume, from the beginning of the stroke to the end of the stroke. To calculate the theoretical value of W air, you must first choose if you're going to use the compression or power stroke. In this case, we chose the adiabatic compression stroke. Using known values, we were able to calculate the theoretical W air values. The experimental value for work air is found using our new work energy equation. Setting points A and B as the beginning and end of the compression stroke respectively, we can calculate work air. This is because we used the value from iFly from part 1. The angular speeds at point A and point B can be found by taking the derivative of the angular position versus time graph and indexing at the appropriate times for the beginning and end of the stroke. Work motor is found by integrating the torque versus angle graph within the stroke bounds, and work friction is the constant that we found before. Here we have selected the data that represents all 4 strokes of our system. We also observe the difference between running the system at low RPM with and without a flywheel. As seen above, when the flywheel is removed, there is a large negative peak in the torque during the compression stroke. This is caused by the lack of kinetic energy required to compress the air. The same phenomenon is observed with the system running at medium RPM. Just like low RPM and medium RPM, during high RPM, the system shows the same behavior with a large negative peak in torque without the flywheel. In comparing the theoretical work air and the experimental work air, during the compression stroke, we can see that they differ by over 60% in the case with the flywheel. This happens because the work on air is much less with the aid of the inertia of the flywheel. Without the flywheel, the motor is doing all the work to compress the air, so the experimental work air values are similar to the theoretical values. Just as in the compression stroke, we see the same behavior during the power stroke. To see the validity of our work kinetic energy model, we compare the work air of the compression stroke versus the power stroke. The sum of these work air values should be 0 if our work energy model is valid. As seen in the results, our model is accurate with the flywheel even though the values obtained are different than the theoretical values for work air in each stroke. This is the case because, as mentioned before, the motor is being helped by the inertia of the flywheel when the flywheel is present. Despite these values being different from our theoretical work air value, they still prove the validity of the work energy model presented in this lab. Thank you.